Alright everybody, welcome back. In this video we're going to talk about linear approximation. And in order to start this off, I want to claim that with the tools that we already have in calculus, we now have the ability to evaluate equations for tangent lines at given points on different functional curves. And so here on this graph I have two functions. I have one in green, which just represents some random function of x. It doesn't matter what it is, it could be anything. It's f of x. And on this graph, I have this point C, which we're interested in, and then I have another equation, y is equal to L of x. And what L of x here represents is the equation of a line that is tangent to f of x at this point C. So it's the line that is tangent to the function f of x at the point C. And I claim that we have the ability to evaluate this already with our tools and calculate it. So let's do it. We know that the equation for a line is going to follow the form L of x here is going to look like mx plus b. That we know. That's just basic algebra. But now we're going to be in the business of seeing what we know about this function already. One thing that we know is that if this is the line tangent to the function at the point c, x equals c, then we know that by definition it's going to intersect this function only once, and that's going to be at the point f of c. And so what that means is that L of c, the function evaluated at the point c for the tangent line and for the function, are going to be equal. So L of c is going to equal f of c. And we also know the slope of the tangent line, because the definition of the derivative tells us the slope of a line tangent to a function at a given point. So the slope of this line, or our m value, is just going to be the derivative of the function f of x evaluated at the point c, and I'm going to notate that as f prime of c. And now if we just plug in L of c here, I would get L of c here on the left side is going to equal f of c, and then I could plug in my value for m here, which is f prime of c. And if we're evaluating L of c, I need to plug in c here for our x value. And then I could add b, and now I have enough information here to solve for my b value. I could just subtract f prime of c times c from both sides. So now, based on this, I have enough information here. I get b is equal to f of c minus f prime of c times c. And now I can rewrite L of x in its final form purely in terms of variables that are based on the function f of x. So I would get m, my m value here is going to be f prime of c multiplied by x, plus, what's our b value here? Our b value here is f of c minus f prime of c times c. And now what I want to do is group like terms, because I see I have this f prime of c times c and this f prime of c times x here, and so I think I could do better by grouping those together. And if you just group these together, you're going to get that the equation for the line tangent to the function at the point x equals c is going to equal f of c plus f prime of c multiplied by x minus c. And so we figured out, using just the tools in calculus that we have already had, what the equation for a line tangent to a function is at a given point. Now I want to make the claim that there appears to be some neighborhood of x values around this point x equals c where the behavior of this tangent line approximates the behavior of the function pretty well. You could think that there seems to be some little range of x values here where the behavior of this line, the red line, is almost indistinguishable from that of the green curve. And in order to demonstrate that, I'm just going to go back to our formal definition of the derivative at this point x equals c. But instead of using the traditional notation that I've been using in this course, I'm going to use something that you might have already seen in a different class, a different video, or something like that. But I'm going to say that the derivative at the point f of c, f prime of c, that's the derivative at this point, is going to be the limit as delta x approaches 0, where delta x is the change in x of f of c plus delta x minus f of c divided by delta x. And the reason I'm going to use this notation is because ultimately what I'm going to do is going to plug in a substitution here. Delta x represents a change in x. So I could think that the change in x would be some x value, some different x value, minus what we started with. And here, since we're dealing with the point c, our change of x would be whatever other x value we were to plug in, minus our original x value, which in this point is going to be the point where we're taking that derivative, which is going to be the point x equals c. So this expression here, x minus c, is going to give us the change in x. And now we know that the derivative of the function at the point c is exactly equal to the limit as delta x approaches 0 of this expression here. But I also want to make the claim that f prime of c is approximately equal to this expression f of c plus delta x minus f of c divided by delta x when delta x is approximately 0. Once again, if this is true, that the limit of delta x approaches 0 of this expression is equal to f prime of c, then f prime of c should be approximately equal to this expression when delta x is approximately equal to 0. And what does it mean for delta x to be approximately equal to 0? That would mean that x minus c would be approximately equal to 0. And so this is this exact same thing as saying that x is approximately equal to c. And I'm going to go ahead and do this. I'm going to make this substitution everywhere in here. Instead of putting delta x, I'm going to put x minus c. And what I'm going to be left with is that f prime of c is approximately equal to f of, let's see, we would have c plus x minus c. And so those c's would cancel, and I would get f of x here. And then I would be subtracting f of c. And then I would be dividing by delta x here, which is just going to be x minus c. And now what I'm going to do is I'm going to multiply both sides by x minus c, and I'm going to add this f of c. And what I'm going to get is that f of x here is approximately equal to f of c plus f prime of c times x minus c. And so what does this tell us? And I'm going to bring this caveat here that when delta x is approximately equal to 0, which is the exact same thing as saying this up here, when x minus c is approximately equal to 0, therefore x is approximately equal to c. So I'm going to bring that caveat down here. I'm going to say when x is approximately equal to c. So when x is approximately equal to c, f of x is approximately equal to this expression right here, which, if you look right here, this expression is exactly equal to the equation we just derived for the tangent line. They're exactly equal. And so what this means is that when x is approximately equal to c, the behavior of this function f of x here is going to approximate the behavior of the line tangent to the function at that given point. And this is just a quick little proof of that. So I can write this here. And here, just to give a little bit more geometric intuition, I've blown up this sort of region around the point x equals c, and you can clearly see that there does indeed appear to be some range of x values. Here I just wrote that for the absolute value of x minus c is less than delta, which from our limits, you would recognize this is just the neighborhood of x values within delta of c. There appears to be some place where the behavior of this tangent line, L of x, is approximately equal to the behavior of the function, f of x. And what this delta value is that will give you that range of x values is going to depend on what function you are approximating. It's going to depend on where on the function you're approximating it. But there will always, by definition of the derivative, by definition of the limit, there's always going to be some range of x values where the behavior of the tangent line is going to approximate that of the function very, very, very precisely. For if that was not the case, then the derivative could not exist at that point on the function. So as long as that function is differentiable at the point, there must be some neighborhood of x values where a tangent line to the function at that point will approximate the behavior of the function. And so let's use this to our advantage and see if we can estimate the value of the square root of 9.01. You might be able to recognize that this is very, very close to the point, the square root of 9, which we can easily evaluate. And so if we take the tangent line to the function, the square root of x, at the point x equals 9, the behavior of that line is going to approximate the behavior of the function, square root of x, very, very well for points that are sufficiently close to x equals 9, which this point is. So let's take the behavior of that tangent line and let's solve for it algebraically. So this is our equation. Remember, we are taking the equation for the line tangent to the function square root of x at the point x equals 9. So that 9 is going to become our c value. And so what we're going to get here is that the equation of that tangent line is going to be the square root of 9, that's just 3, plus the derivative of the function at that point. What's the derivative of the square root of x? The square root of x, that's just equal to 1 over 2 times the square root of x. And so plugging that in, 1 over 2 times the square root of 9 is going to be 1 over 6. So we plug in 1 over 6 here. And then we're multiplying by the value that we are estimating here, which is 9.01 minus 9. And if you work this out, this is just going to be 3 plus 1/6 of 0.01. So this is going to be equal to 3.001666, repeating forever. And if you take the accepted value for the square root 9.01, I'll just plug this into our calculator, we get that the actual value is equal to, looks like 3.001666204 ... And so you can see that these two are very, very close. And we were able to approximate it using just simple algebra with this tangent line. Now what I want to do is point out that there is an alternative way that we could have derived the formula for this tangent line. And it's going to lead us into a new concept, so it's worth exploring. What do we want in a tangent line? What we want in a tangent line is we want that the formula for the tangent line will evaluate to the value of the function at the point where the tangent line is tangent to the function. And so what's a nicer way of saying that? The nicer way of saying that is to say that the function of the tangent line evaluated at the point where it is tangent to the function must be equal to the value of the function at that point. Or in other words, if L represents the function that's giving us our tangent line, L of c must be equal to f of c, where c is the point that the tangent line is intersecting the function. But what we also want is for the slope of this tangent line to equal the slope of this function at that point. And so what is the slope of the function at that point? Well, that's just f prime of c. And if a line has a constant derivative, a constant rate of change, then the slope of the line at any point is always going to be equal to the slope of the line at any other point. And so another way to say this is that we don't have to write L prime of c here, we can write L prime of x. The first derivative of this formula for the tangent line here must be equal to the derivative of the function f of x evaluated at the point x equals c. And with this, I think we have enough information to derive our formula for the function L of x. Because we know that it must be equal to f of c when you plug in the point c, x equals c. And so that's taken care of now, because if we plug in any value into this function, this rudimentary function here, it's going to equal f of c. But that's not exactly what we want. What we want is for that to happen at the point x equals c, but what we also want is for the first derivatives of the functions L of x and f of x to be equal at the point x equals c. And in order to add that constraint, I'm just going to add a factor of f prime of c, and then I want this to stay when I take the first derivative. And so I want to add some variable here such that when I take the first derivative of this function, that will go to 1. And what has a derivative of 1? Well, that's just x when we're dealing with the variable x. And so I'm going to add an x here. Now, when I take the first derivative of this function L of x, I'm going to be left with f prime of c, which is exactly what we want. But we're not quite done, because if I was to plug in the x value c here, I would get, let's see, L of c would equal f of c plus f prime of c times c. And that's not what we want. We want f of c. And so I'm going to add this constraint here. Then instead of x here, I'm going to put x minus c, such that it does not change the value of the first derivative, but allows us to have a function where when we plug in the point x equals c, this will go to 0. And then we'll be left with f of c. And when we take the first derivative, we will get f prime of c. And the reason that it's worth exploring this alternative way of constructing this formula for the tangent line to the function at the point x equals c is because this opens us up to new possibilities. Because what if we wanted a function where it wasn't just the first derivative that was equal, but also the second derivative? So you could think of some sort of tangent quadratic. And so let's do that. Let's say that this is the function q of x, and so we want q of c to be equal to f of c. And we also want q prime of c to be equal to f prime of c. But we also want to add the constraint that q double prime of x is equal to f double prime of c. And now let's construct a function given these constraints and see what we get. Well, I'll claim that for the first two parts of this formula, it's going to be the same as the linear approximation. We're going to get that q of x is equal to f of c plus f prime of c times x minus c. And that's going to take care of these first two constraints, that the function at the point f of c is going to be equal, or at the point c, the value of the q function is going to equal the value of the f function. It's also going to take care of the constraint that the first derivatives of those functions will be equal at the point x equals c. But now we need to deal with this constraint here. And so in order to do that, I'm going to put f double prime of c here. And then what's a variable or a function where if I take the derivative twice, it will evaluate to some constant? Well, that would have to be some sort of function that's being squared, because when you take the first derivative, it becomes linear. When you take the second derivative, it becomes constant. And so I want to add a squared variable here. I learned from my mistakes last time. I'm not going to put x squared. I'm going to put x minus c squared, such that when I plug in the point x equals c, this function will still evaluate to f of c. But we're not quite done here, because if you were to take the derivative twice, what would happen? Well, the first time you take the derivative, this will go to 0. We'd be left with f prime of c plus, let's see, we would get f double prime of c times the derivative of this. That would be multiplied by 2 times x minus c. Now when you take the derivative the second time, this will go to 0, and we'll be left with 2 f double prime of c. This is not what we want. What we want is for the second derivative to equal the second derivative of the function. So we need to add an additional limitation on this formula here. We need to put f of c back. And what we need to do is add a factor of a half here, such that when we take the second derivative, we will get f double prime of c. And this is our formula for a quadratic approximation. And notice here, the first derivative is only equal at the point x equals c, because now this is a function where the first derivative is subject to change. If you take the first derivative here, q prime of x is going to equal f prime of c plus f double prime of c multiplied by x minus c. And so, yes, at the point c, this will be equal to the first derivative of the function f evaluated at c. But at other points, this is going to change, because now we're dealing with a sort of, you could think of this as a tangent quadratic. It's the quadratic estimation for the behavior of a function at a given point c. And so this is going to allow us to hone in a little bit and get even more accurate estimations where it is demanded by different problems or situations in real life. Alright, now what I want to do to end this video is find linear and quadratic approximations for cosine of x near the point x equals 0. And the reason I want to do that is because it's going to come up with two different equations. I can plot both of them, and we can look at the differences. We can see how much more accurate the quadratic approximation is versus the linear one, and where you might want to use the linear one versus the quadratic one. And so in order to do that, it's sometimes useful to sort of keep track of these derivatives in a table, especially when we're dealing with two different equations which are going to use many of the same values. And it's also useful in pointing out that when we're dealing with the point x equals 0, what this is going to reduce to is that our equation for the linear approximation, or the tangent line at the point x equals 0, this is going to reduce to f of 0 plus f prime of 0 times x. And similarly, our quadratic approximation is going to equal f of 0 plus f prime of 0 times x. That's just our linear equation. It's the exact same. But then we're going to add this additional factor, f double prime 0 over 2, once again multiplied by not x minus c here, because we're dealing with c equals 0. I should rewrite this. We're dealing with c equals 0, so this is just going to reduce to x squared. And so now with this information, what I'm going to do is just differentiate cosine of x twice. First, before we do that, what is f of c here? Well, that would just be cosine of 0. That's the point of interest. And so this is equal to cosine of 0, which is just going to be equal to 1. And then f prime of c here is going to equal, what's the derivative of cosine? That's just negative sine of 0. And what's negative sine of 0? Well, that's just going to be equal to 0. And then we'll take the derivative of the first derivative, which will give us the second derivative. The derivative of sine of x is just cosine of x. We have this negative out front, so this is going to be negative cosine of 0, and that's just equal to negative 1. And so here, our tangent line approximation, this is going to be given by the equation. We would plug in f of 0 here, we'd get 1, and then f prime of 0 is just going to be 0. And so this whole thing will reduce to 0, and we'll be left with just a simple horizontal line at the point y equals 1 for our linear approximation. But let's see what we get with our quadratic approximation. These first two terms here are just the linear approximation, so we could just add that. So we're going to get 1. But what are we going to get for our second derivative here? We have our second derivative of the f function, so that's going to be f double prime of c is just negative 1 divided by 2. So we get minus 1/2 x squared. And so this is going to be our quadratic approximation. Now I'm going to get some graphing calculator images, and I'm going to put it on here so we can see the difference. And we're back. I just went into Desmos really quick and plotted both of these equations. So in red on both of these graphs, I have cosine of x. And then in blue, I have our linear approximation here, which is just a straight line. And you can see that around the neighborhood where x is approximately equal to 0, this still does do a very good job of approximating the value of the function cosine of x. But once you get out here, it quickly falls off. Once you get to the point x equals 0.5, it's not even similar. Whereas here, our quadratic approximation, although it still is very accurate around the point x equals 0, it maintains that level of accuracy well beyond the point of x equals 0.5. It still is very, very close to the behavior of the function at that point. And so I've sort of marked in these with these orange dotted lines about the range of x values which are cleanly approximated by these different approximations. And so the key to realize here is that it's not always better to use this quadratic approximation, because if, for example, you are dealing with this range of x values here, then it doesn't really matter which approximation you use, so you might as well use the simpler one. It will save computing power, it will save work, it will save effort. But if you are dealing with x values out here, for example, then it doesn't make any sense to use this linear approximation. It's not even going to get you remotely close to the accurate answer, and then you might need something a little bit more accurate, like our quadratic approximation here. So I hope that was interesting. I hope these concepts of linear and quadratic approximation are illuminating, at least to some extent. You can see where you might want to use this in the real world, where these approximations give you a much simpler, cleaner version of the actual function than you might otherwise have to deal with. So I'll see you guys in the next one. Thanks for watching.